from the William Tell Overture, named for this fellow, a Swiss folk hero that's like Switzerland's version of Robin Hood. He was skillful with a bow and disrespectful to nobles and stuff like that. His most famous feat is shooting an apple with a crossbow off of his own son's head. He did this because he was a show-off and a bad father. But he gave us a famous problem in physics, which is what happens if you shoot a projectile at an angle and it lands at the same height from which it was launched. So if our initial velocity here is in that direction at some angle here, theta, and here's the path of our projectile, the parabolic path, and it returns to the same height it was launched at. What can we learn about that projectile? The question of interest, of course, to Mr. Tell was what angle should he shoot at in order not to murder his own son. So let's look at the information we have available. You would know that the launch speed from the bow is about 90 meters per second. So that bolt is coming out at 180, 200 miles per hour at a distance, standard Olympic archery distance of 70 meters. Our given and unknown information. Let's examine. So we know, once we identify our two events, event 1, launch, event 2, apple/possible death, that the change in x-coordinate between them, we know that, 70 meters. We also know the change in the y-coordinate. That's the key piece of information here. Well, it's launched at some height above the ground, and it lands at the same height above the ground. So final minus initial is 0. Delta y is 0. That's sort of the defining characteristic of our William Tell problem here. We'll also know the x component of the velocity. Let's see if we put in our components to our velocity triangle here. There's Vx. We know that'll be constant at all moments while the bolt is in free fall. And then this is V1y, the y component of the initial velocity. So if cosine theta is Vx over the speed, then Vx equals the speed times cos theta. We know both these values, so we know Vx, and then the y component of the initial velocity. Since sine theta is V1y over the speed, this will be the speed times sine theta. Okay, we know all that information. What we don't know is the time that the bolt will be in the air. And oh, wait a moment, we don't know the angle. That's the whole point here, to figure out the angle. So actually, we don't know Vx, and we don't know Vy because we don't know the angle. We need to move both of those into the unknown category. But we at least have the initial speed. Okay, so let's look at our equations and see what we can do with this information. We want to know, let's see, well, we know delta x. We don't know the time. We don't know Vx there. Okay. We know delta y. Don't know the time. Don't know V1y. Don't know the time. The change in speed, not sure about that. Don't know our final y component. Again, don't know the time. Don't know the final y component. We do know that. Aha! There's something at last we can solve. We could get the final y component using this. However, I have a different plan in mind. Let's actually see what we can do with these two equations in this case and set up a little system. So, starting with this relationship right here. Delta y Trust me, I know what we're doing here. Delta y is v1y delta t minus 1/2 g delta t squared. Okay, we know that delta y between events 1 and 2 is 0. And that allows us to simplify this equation considerably. If this is 0 right here, then we can divide both sides by delta t, and that delta t will drop out, and one of these delta t's will drop out, leaving us with 0 equals v1y minus 1/2 g delta t. So we can solve for the time. Delta t is going to be equal to 2 v1y over g, once you do a few steps of algebra. Okay, now we know the time. As usual, we can import that over to the horizontal part of the problem. So I'm not going to put any numbers in yet. Let's just keep working with variables here and go to the other horizontal equation. Delta x is vx times delta t. Let's substitute this expression in here for that delta t. That gives us delta x equals vx times 2 v1y over g. Okay, it may seem like we're not really getting anywhere here because we don't know vx and we don't know v1y because we don't know the angle. But let's rewrite both of these in terms of the angle. So delta x equals, I'll bring that 2 out front, and vx we know can be written like this, and v1y can be written like this. So vx is the speed, initial speed times cosine theta. v1y is the initial speed times sine theta. All that's over g. I'm going to write that once more. Put these two speeds together. 2 times the initial speed squared. Actually, I'm going to put this 2 over here next to 2 cosine theta sine theta. All of that over g. Now, I pull a little trick out of my hat. A trigonometric identity. This expression, 2 times sine theta times cosine theta, can be shown is equal to sine of twice that angle. We can replace this with sine 2 theta. If we do that, we find that delta x equals, I'm going to come back up here, delta x equals the initial speed squared, 2 cos theta sine theta becomes sine of 2 theta all over g. I'm going to rewrite that. It's a little messy because this is an important equation. This is the William Tell equation. It only applies to this scenario, but it's sort of famous. Let's put a box around that. What this relationship tells us is that if we launch and land at the same height and launch at a certain angle, the distance that we will travel, our range, is equal to our launch speed squared times sine of twice that angle all over g. So we can relate the launch angle directly to the range. One thing you can do with this equation is determine what angle will give you the maximum range. What angle should you fire at to make the projectile go as far as possible? You may have an instinct about what that answer is. Can you use this equation to prove what that answer is? What angle here gives you the maximum range? I'm not going to solve that problem right now. I'll leave you to think about it. But what we want to know here is this angle for William Tell's situation. So can we solve for this angle? Because we know these other things. We know delta x, 70 meters, and we know the initial speed, and we know g. So let's rearrange this to solve for that angle theta. I'll multiply both sides by g, divide both sides by v1 squared. So that gives us g delta x divided by the initial speed squared equals sine of 2 theta. So I can write that as 2 theta equals the arc sine, use that function on your calculator, of g delta x over v1 squared. And then lastly, divide both sides by 2 to solve for theta. Theta equals 1/2 arc sine g delta x all over v1 squared. There we go. And that's how we can solve for our angle in this situation. If we put in our values here, 70 meters and 90 meters per second, and 9.8 there for g, we'll find that that angle comes out to 2.43 degrees. A tiny angle to pull off a tremendous and stupid feat.